Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with your homework and prepare for your test. So we're going to take a look at a few of the problems in your homework here, starting with number 16. So number 16, it says something about water falling off of a waterfall. And the idea is that when the water falls off the waterfall, it speeds up. It has a certain, pardon me here. All right, I'm back here. So the idea behind 16 is that the water, if I imagine a mass of water here, now I know the first question you're going to say is, but there's no mass given in the problem. You have to just look through that, right? Just because there's no mass given in the problem doesn't mean this water does not have mass. So you just, imagine maybe a cup full of it. It's got a certain mass m, which would mean it has a potential energy equal to mgh, measured from the bottom. Now, that means that the kinetic energy at the bottom, 1/2 mv squared, basically would equal the potential energy here, mgh. Then the idea is this water interacts, it basically splashes down here, slows down again, and then the idea is, well, where did that energy go? Well, some of it went towards increasing the temperature of the water. So for temperature increases, you've got Q equals mc delta T. And when the part that says assume all of the kinetic energy, which is equal to the potential energy, gets absorbed, basically that's going to be your heat term. The masses will divide out. You'll be able to solve it for the delta T. Okay, let's talk about 17. Get rid of this. All right, in 17, let's see, it says an aluminum bar is raised by 10 degrees when it absorbs a certain amount of heat. So there's some sort of aluminum bar. Let's start with maybe a picture of that. It absorbs some amount of heat, which is given in the problem. Its temperature goes up, so that's a specific heat question. Q equals mc delta T. And all the values here are given in the problem. They tell you this, they tell you this, they tell you the delta T. So it's just a matter of solving for the specific heat. If you're having trouble getting the units, or if you're having trouble getting it to work, watch those units carefully. Notice in the problem it says kilojoule per kilogram degree centigrade. So watch that. 18, where it says Lake Erie contains approximately 4 times 10 to the 11th cubic meters of water. How much energy is required to raise it from 11 to 13 degrees? All right, so they don't tell you a mass, they tell you a volume in number 18. The mass and volume are related by density. So density, if you're not familiar with this, is mass per unit volume. Density is m over v. And the density of water is 1,000 kilograms per cubic meter. They gave you a volume, basically just multiply and that'll give you the mass. And then for part A, it's an mc delta T problem. Q equals mc delta T, where this is going to be the mass you find up here, specific heat of water, delta T given in the problem. Part B, where it says how many years would it take to supply this using a certain, mine says 800 megawatt, yours might say something else, exhaust energy from an electric power plant. So this 800 megawatt, mega means 10 to the 6. So this is 800 joule per second. And that's a unit of power. And remember, power is rate that energy is transferred. So that's a change in energy over a change in time. After you calculate a value here, use that for the change in energy here and solve it for delta T. You're going to find that it's probably a very, 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 very large number, and then you're going to have to convert it to years. So that should be enough with 18. 19, a 2-gram copper coin at 27 degrees is dropped 45 meters to the ground. All right, so imagine this coin. Oops. Starts up here. Here's my coin. They give you a height here. In my example, it says 45 meters. Yours might be something else. The coin is dropped, so it's going to accelerate down. Here's a picture of the coin right before it hits the ground. Write out a work energy theorem. Well, actually, you don't even have to do that, but I'll just say this. The potential energy, PE1, is going to equal the kinetic energy, KE2. Then the coin hits the ground, and you'll notice that after it hits the ground, eventually it's going to rest. And then the million-dollar question is, well, what happened to that kinetic energy? And the answer to that is, when the coin hits the ground, it's going to deform the coin a little bit, going to deform the ground a little bit. That kinetic energy gets absorbed kind of in this region, some by the ground, some by the coin. It says in the problem, assume 70% of the gravitational potential energy goes towards increasing the temperature of the coin. So take 0.7 times PE1. Yours might actually be 60% or another percent, but and then use it for the Q in the MC delta T term. Use it for the Q in this equation, where the M is given in the problem. They tell you it's copper, so you can look up its specific heat, and the temperature change is what you're looking for. Actually, what you're looking for, it says, is the final temperature. So calculate the temperature change from this, and then add it to your original temperature, and that'll get you the final temperature. Um, 20 is a unit conversion, basically. Let me get rid of this stuff here that I don't need. Number 20, it says a 48 kilogram woman cheats on her diet, eats 511 calories. Now, your numbers might be different, but mine says 511 calories. So a calorie is a unit of heat. This is a big C. There's two different types of calories. There's the standard calorie, which is 1 calorie is equal to 4.186 joules. That's just a conversion factor. Then there's what's called a food calorie. A food calorie, which is denoted with this big C here, is a kilocalorie. So 1 food calorie is 4,186 joules. So this is the conversion you're going to need for this problem. So take your energy in calories and just convert it to joules for part A. Part B, how many stairs must she climb if each stair is 15 centimeters? So when this person goes up the stairs, every time they go up a stair, they're going to change in potential energy by an amount mgh, where the h is the height of each stair. So if you calculate this value, you're going to get a number with units of, let's say, joule per stair. And then if you multiply by the number of stairs, you'd have how many joules of energy were used, and just set it equal to your energy for part A. Part B, if the human body is only 25% efficient in converting chemical energy to mechanical energy, how many stairs must they climb? Well, let's say that our energy out, that's what I'll call it, the energy used, if you were 100% efficient, the energy out and the energy used up by the person would be the same. At 25% efficient, that means the energy output is 0.25 times the energy used. If something's 25% efficient, what that means is if I take how much gets used up and multiply by 0.25, that would give you how much work or energy output the person could do. So in part C, take your answer to A, sub it there, and then solve for this. And then use your conversion factor for between joules and how many joules per stair to figure out how many stairs she'll have to climb. '21. Let's chat about 21. Okay, it says a 78 kilogram sprinter accelerates from rest to 11 meter per second in 4.6 seconds. Calculate the mechanical work done. Well, basically, you can do that from the work energy theorem. you've got PE1 plus KE1 plus work equals PE2 plus KE2. There are no substantial changes in height in this problem, so I would throw away the potential energy terms. And it says accelerates from rest, so the KE1 term is also 0 in this problem. So part A, where it says calculate the mechanical work done, that's just going to be a 1/2 mv squared term. You're going to get it from this. Those numbers are all given in the problem. Part B, calculate the average power the sprinter must generate. So power, remember, is the rate that work is done. It's equal to work over time, or change in energy over change in time. Both of these are equal to power because the work and the change in energy are the same thing. And you can see that right in this equation here. The work is equal to KE2, and the KE2 is the change in energy for the system. So take your kinetic energy, divide by the time, you'll get the average power. Part C, where it says if the sprinter can convert food to mechanical energy with an efficiency of 25%. So basically what that means, right? All people, this is kind of how it works. You take an energy in the form of food. I'll put E in. Then as a person walks around, lifts up their coffee, runs, they do work. And what the person does is, your body basically takes the energy from the food and converts it to work, right? We're going to talk more about that next week. Your body it can be modeled as what's called a heat engine. Now, if your body was 100% efficient at doing that, that means that for every, say, 100 joules of energy you eat, you can do 100 joules of work. But nothing is 100% efficient. It just doesn't work like that. If your body has an efficiency of 25%, that means that only 25% of this can be converted to work. So your work is going to equal your efficiency, whatever that is, times your energy intake. So in different problems, you could have different values. Mine says 25%. If it's 25%, this would be a 0.25. If it's 30%, it would be a 0.3, and so forth. So I'm going to chat about one more here because I'm running out of time. Let's chat about number 22, where it says a lead bullet traveling at 390 meters per second is struck or stopped by a tree. All right, so we've got a bullet. It's moving along. It's got a certain speed given in the problem. There's a mass there, so you can calculate a kinetic energy and get a number. Here's my tree trunk here. Bullet hits the tree. Basically, it probably puts a hole in the tree, something like that. Now, you'll notice that the kinetic energy after it stops is 0. So then the million-dollar question, where did this go? Well, some of it is absorbed in the form of internal energy in the material around here, and some of it in the bullet itself. It says in the problem to assume half is transmitted to the tree and half is transmitted to the bullet. So take this number, cut it in half, and we're going to assume that's how much energy is absorbed in the bullet to increase its internal energy and in effect raise its temperature. So take that kinetic energy, divide by 2. Now for the temperature part, that's going to be a specific heat problem. Q equals mc delta T. Take this number, use it for the heat term, and then you've got an mass is given. This is lead. You can look up its specific heat, and then you can solve for the delta T. One thing to point out, because again, I know it just stops people whenever masses are not given, but that mass does not need to be given to solve this problem. Even if that mass were not given, the kinetic energy would be 1/2 mv squared. Half of that would be 1/4 mv squared. And if you put this here, the resulting equation would look like 1/4 mv squared equals mc delta T, and these would divide out again. So, moral of that story, don't stop on a problem just because you don't have a mass. All physical things that you can see or observe have mass. If it's not stated in a problem, just put an M next to it for whatever the mass is and move on. That's my advice on those. So, folks, that's all I got time for right now. I've got a bunch of middle schoolers coming here in about 10 minutes. I got to give them a tour of the place. So I know these videos were a little quick. I'm hoping they give you a fighting chance to get quite a bit done. I'll see you folks on Monday. Have a great day.